Find the polar form of the vectors negative 3j and negative 2i plus 5j. So if you have some vector v, then the polar form is written like this: r times cosine theta comma sine theta. So cosine theta comma sine theta for any angle theta is going to be a unit vector, because cosine squared theta plus sine squared theta is equal to 1. And then r will be the magnitude of the vector, and that will be greater than or equal to 0. Actually, it'll be strictly greater than 0. The only time the magnitude of a vector is 0 is if the vector is the 0 vector, and the 0 vector has no angle associated with it. So the polar form of the 0 vector is just itself. It's also 0, 0. Okay, so the first vector is negative 3j. So negative 3j, that's shorthand for the vector 0 comma negative 3. And the magnitude of this vector is 3. Using the formula, it's the square root of 0 squared plus negative 3 squared, which is the square root of 9, positive square root, so 3. So r will be 3. So this vector 0 comma negative 3 is going to be 3 times cosine of the angle of the vector, sine of the angle of the vector. So let's draw the vector. 0 comma negative 3 is there. So this is our vector, negative 3j. That's the number negative 3 on the y-axis. And for the angle, there's technically infinitely many angles that will work. So we'll take the angle negative pi over 2. So this is 3 cosine negative pi over 2 comma sine negative pi over 2. And the cosine is 0 and the sine is 1. So the sine is negative 1. So 3 times 0, negative 1. But the important thing to do here is identify in some way, shape, or form the angle, negative pi over 2, because the vector has direction and magnitude. The magnitude is 3, and the direction can be described in terms of an angle. Okay, for the second one, things are a little more complicated. Negative 2i plus 5j. Which is the same as the vector negative 2 comma 5. The magnitude of this vector is the square root of negative 2 squared plus 5 squared, which is the square root of 29. So that will be r. So we're going to write this vector negative 2 comma 5 as being the square root of 29 times the cosine of some angle theta times the sine of some angle theta. Now in this case the angle is not going to be an angle that we recognize, so let's just find some form for it using the inverse tangent function. The inverse tangent. So let's see, the vector negative 2 comma 5 is in the third quadrant, second quadrant, and we want this angle theta. So the tangent of theta, if this is the point xy, the tangent of theta is y over x, and so the inverse tangent of theta of y over x will be theta. So the inverse tangent of y over x is the angle that we like. Well, there's one small problem with this. This is not exactly accurate here. The inverse tangent function will only output values that are between negative pi over 2 and pi over 2. You see, our vector here is in the second quadrant. There's another vector here in the fourth quadrant directly opposite it with coordinates negative x, negative y at the final point. And if you do the same ratio of the second coordinate divided by the first coordinate, they'll be the same because the negatives will cancel. So y over x for this point and y over x for this point are the same. When you do the inverse tangent of that ratio there, you'll get this angle, which I'll just call phi for the sake of argument. And that's not the angle that we want. So when your terminal point is in the second quadrant or the third quadrant, then the inverse tangent doesn't work directly. So this is not quite right. What theta is you have to add 180 degrees to it because the inverse tangent is giving you the corresponding vector in the opposite direction. So we have to add pi 180 degrees plus the inverse tangent of 5 over negative 2, negative 5 halves. So this is theta. So we can now say that the vector negative 2 comma 5 was its magnitude, square root of 29, times the cosine of theta comma sine theta, where theta is this angle, which will be in the second quadrant.